So, hello friends. Today I have another topic, that is statistical description of system of particles. So here what we will be studying. So our first topic will be the specification of state of a system. So how do we define a state of a system? So basically, if you see in classical mechanics, in case of classical mechanics, the state is defined as the position as well as the momentum coordinates. So basically, if you have the information of, basically, if you know the position of the particle as well as the momentum of the particle, then you know the state of the particle, where it will be or where it was before. How? Using Newton's law. Using Newton's law, you can find the state of the particle or the system. Now, in case of quantum mechanics, how do you define the state of the system? You basically the state of the system is basically defined by this wave function x and t, which is governing by the Schrodinger wave equation. And what does this wave function signifies? This the modulus of this uh, wave function. This will signify the probability density of finding the particle between, let's say, x to dx range, x to x plus dx range. So that is how we define the state in the quantum mechanics. Now, in case of classical mechanics, basically the statistical mechanics, in case of statistical mechanics, we define the state of a particle by the phase space. Phase space is nothing but the space created by the position and the momentum coordinates. So basically what you have two axes, each representing position and momentum coordinate. And a state will correspond to a single point here. Let's say this x comma p, xi comma pi, let's say. Now, what you will see here in the statistical mechanics, how this state, this point is moving with respect to time. So that is how you define the state of a system here. Okay, so now let's see a single particle state. Basically, in the how this is behaving in 1D. So basically, the phase space. The system can be completely described in terms of its position coordinate, basically q, and its momentum p. So if you know the information of the position coordinate, and if you know its momentum, then you know it. Then you know about the system completely. Now, it is possible to represent the situation geometrically by drawing the Cartesian axes, just as I showed here. Now, the position as the position of and the momentum of the particle changes in the time, this represents points moving through this phase space, just like this. First, at some time it is here. After some time it will be here. Initially it could be here. It could be here. So this will track with trajectory. It is showing like a parabola, right? So this is space, what is created by the momentum and the position axis, as a phase space, and it has a what we say unit volume. The unit volume will be defined as this delta of q, delta of p, and this will be about the h naught, that is some small quantity. Okay. Now let's see what an statistical ensemble is. So basically here we will be discussing about the systems in terms of probability concept. So that is the beauty of statistical mechanics. Basically, you describe all the parameters, macroscopic parameters, based on the probability concepts. You will define the system based on the probability concepts. So now, here we will be focusing on the ensemble, which will be consisting of a large number of identical systems identical as well as non-interacting. So the systems will be not interacting as well as identical systems, and the number of such systems will be a large number. Uh, Now, the system in this ensemble will be in different states and will also be characterized by different macroscopic properties. Different macroscopic properties mean, let's say, energy. They will have some energy, and in that particular energy, you may have different states. But we can ask the probability of occurrence of particular value of such a parameter, just like we can ask what is the probability of having this much energy or this much magnetic moment, let's say. Magnetic moment is also a microscopic parameter. So we will be discussing this. This particular statement will be much clearer when we do a problem here next. Now, using this probability calculations, we will be calculating these microscopic properties of the system, just like energy, let's say, entropy, let's say, magnetic moment. If I say magnetic moment, and many more things related to this, basically magnetization, etc. Now, let's see. I told you we will be discussing an example. So basically, here we have three spin half particles. So three spin half particles meaning, so you have three spins. Each of them could be either up or down. Okay. So how this system can arrange itself in different particular combinations. So let's see that. So the value of the quantum number, basically the magnetic quantum number m, it can take value plus minus s. So where s is this half, right? So in this case, it can take plus minus value half. Basically, in this range, actually, it takes magnetic quantum number. The value of magnetic quantum number will be from s to minus s. So here, in this case, it will be plus minus half. So plus minus half will be the magnetic quantum number for this spin, this first spin, the second spin, this third spin, right? So what will be the different combinations? As I told you in the random walk problem also, there you have two choices, either left or right. Here also we have two choices. The moment can be either in up direction or in down direction, right? This up is represented by ms value half. This down is represented by ms value minus half. So here, if all the spins are along the up direction, then ms value will be half, half, half for the three spins. And then the net magnetic moment, when all these three magnetic moments will point in the same direction, that will be 3 mu. And the energy corresponding will be minus mu net, let's say, and the magnetic field. So the magnetic field direction is in this direction, along this direction. So that is the one possible case. What could be the another case? Let's say this particular spin, it flips into this particular situation. Then what will happen? So then we will get this situation. So we have this particular combination, and if you keep on doing this, you can complete this table by yourself. So basically, what we have total energy as minus 3 mu h, or we have minus mu h, or we can have total energy, which is a macroscopic property of the system, or it can be 3 mu h. So basically, we have four possibilities of getting energies. But how many combinations, basically how many different distributions the particles can be? The total the distribution is 8, basically 2 raised to power 3, right? Okay, so this one particular state with one particular energy level, this will represent microstate 1, and then this another set of arrangement which corresponds to the same set of energy, that will correspond to some different microstate, and the same will go on. Whereas this, if you see this particular value, this arrangement, this arrangement, this arrangement, these all represent different microstates. Okay, so now I have a question. The question is, what is the probability of getting all these states, or basically the energies? So I have minus 3 mu h. Out of these 8 possible different ways, I am getting this minus 3 mu h, basically this much energy. How many times? Only one time. So the probability of getting this particular energy will be 1 divided by 8, right? Now, what is the probability of getting minus mu h? So that will be 3 by 8. The same case with mu by h, and 3 mu by h will be 1. And now if you add all these 3 probabilities, you will get 1, right? You will get 1 definitely. So these are this is about an example, a physical example, where you have a set of 3 magnetic spins. Okay, so let's move forward to the next slide. So now, next we will be studying about the basic postulates related to basically the equilibrium. So first of all, what we are going to discuss is the uniform distribution of microstates. So whenever there is a thermal equilibrium, so this thermal equilibrium implies that the distribution function, the probability distribution function, which is given by rho as a function of momentum and space coordinate, position coordinate of the system, will be a function of energy. So what does this mean? This means that this distribution function will be a function of Hamiltonian. You will see in the later problems also that this probability distribution function we have to find as a function of this Hamiltonian. And this equilibrium also signifies that the probability of finding the system in any one of the states. So basically we have n number of states, right? So the probability of finding the system in any one of these states is independent of time. So basically the probability will not depend on time. Just for an example, so basically this rho as a function of time will be, if I differentiate it with respect to time, then it should give me 0. And you can also write this as a by the chain rule as del rho by del h and then E dot, where E dot is the time derivative of E with respect to time. Now, what does this mean? If you see my previous example here, so in this case, the probabilities were some finite number. They were independent of time. So if this is the 1 by 8, basically this is the situation when equilibrium is. So if the system is in equilibrium, then this microstate 1 will correspond to this probability only, and this microstate 2 will correspond to this much probability only. So there is not a time varying probability when the system is in equilibrium. Now, the last and important postulate is that in any isolated system which is in equilibrium and that will be equally likely to be in any one of its accessible state. Now, again, let's see this by example. So basically, this is a isolated system of 3 spins. So now, here you have 8 accessible states for the system to be in. Where these M1, M2, M3 values can take any of these eight combinations. Now, whether it is this state, this state, this state, this state, and the rest of the states, they all will have the same probability. That is what is coming from the principle of equal priori principle. So, what does that mean? that all these 8 states, they all will have the same probability. They all will have the same probability, that is 1 by 8. Okay, so now, and it is this microstates, therefore they are uniformly distributed, right? And that can only happen when the system is in equilibrium. So these are the postulates regarding the equilibrium. And if 1 by 8 is the probability related to this microstate, and that will be the probability of this macrostate also, right? Now you have in macrostate 2, you have 3 such states. So the probability will be just a multiplication of these 3 states. So that will be 3 by 8, and similar will be followed by the rest of the states. Okay, so I hope you understood the concept of these basic postulates. So how equilibrium is defined in statistical mechanics. So first of all, what was the thing? That the distribution function will be a function of energy. The second thing is that this probability of finding the system in any one of the states will be independent of time. And then the third one is that any isolated system which is in equilibrium, that will be equally likely to find in any one of the accessible states. So these are the postulates. You must remember this. So now let's see how to approach this equilibrium, how this equilibrium condition is achieved. Let's suppose we don't have a system where this isolated system, which is not equally likely to be found in any one of these states. So let's say we have all the 4 microstates, right? All let's say all 8 microstates. Out of them, let's say this where all the spins have half this condition. Let's say this is more favorable. Favorable in the sense, initially it was 1 by 8, but let's say it is not 1 by 8, then it is 2 by 8. Then what will happen? So this means this situation cannot happen at equilibrium. If the system is in equilibrium, then all these states has to be equally likely, right? And if it is so that if the probability is coming to be 2 by 8, that means the system is not in equilibrium, and this situation has to change with respect to time. Now, this also means that this distribution of system, whatever the distribution of the over the accessible state, should change with respect to time, and correspondingly, the mean value, basically the expectation value of various microscopic parameters, which is describing the system, will also change. That is, let's suppose this average value of energy, right? If it is not in equilibrium, then this value must change in equilibrium, right? Okay. So now there also exists a finite probability that the system will be at some later time be found in some other state accessible to it. So basically, if the system is in this configuration, let's say up and down, now then there exists a finite probability that this particular system, it may change to up, the center one will be down, and the last one will be up. So basically, these 2 spins, they interchange their what we say, this polarity, let's say. So there exists some finite probability of doing so. And now this transition of states is being caused by the presence of some small residual interaction between the particles. Okay, so like here in this case, it may be some spin interaction, and in some other case, it could be other. So this is how the equilibrium is achieved. Now let's see the probability calculations. So consider a system which is in equilibrium again and isolated. So if it is isolated, then its total energy is known to have a constant value between some range, let's say E to delta E plus delta E, right? Then let's suppose this omega of E, it denotes the total number of states accessible to the system in this range. So basically what you have E and E plus DE. So actually we are considering where there are a number of states in between this energy range accessible to the system. Now, the number of states in this range, I'm saying it is omega of E. Omega is E is the total number of states in this range. Okay. Now, for any microscopic system, even a physically very small interval, basically this very small interval, this interval is delta E. This interval delta E contains many possible states of the system. Therefore, we shall denote delta E as the number of states whose energy lies between E and E plus delta E. Now, this delta E, basically how many number of states will be in between this range will be proportional to this range. If I make this delta E large, this delta is E. If I make it this large, then I have a lot more energy accessible states, right? So this delta E, this omega E must proportional to delta of E. And if I remove the proportionality constant, this I'm denoting this by rho of E. Now where this rho of E is nothing but the density of states. It is density of states. Now, this density of states will be definitely independent of size of delta E. Whether I choose this delta E or this delta E, this rho, basically the density, will remain the same. Okay, so now let's try to do a problem based on the previous, what we call this, postulates. So the example is, if there are four identical molecules in a 1D container, and it is given that the molecule can be found in either right or left end of the container. So here you have a container like this, and let's say this is left part, this is right part, and you have four particles, and all of them are identical, right? And this particle, it could be either on left, either on right. Okay, so now the first part of the question says that what are the possible number of configurations? What could be the configurations and their number of ways? So, and their corresponding probabilities of each configuration. So let's first do this problem A. So here you have the situation. Here you have the container, right? Now let's say the number of the number of particles which are on the left. Let's say they are n, and which are on the right. Let's say that they will be n minus n. Now, in how many ways we can arrange n particles out of total n, capital N, how in the two sides of the box? So that will be given by nothing but n Cn. Basically, the combination formula n factorial divided by small n factorial and capital N minus small n factorial. Now here what we have is four molecules, and you have two sides of the container. Again, this problem is very similar to the random walk problem. You have two situations. The particle can be either on left or right. And now there are four such molecules. So the combinations will be 2 raised to power 4, that is 16. So the number of ways total, the number of ways of arrangement of these particles will be 16. Okay. Now how this combination configuration will look like? Let's see this. So basically the first configuration is all the four particles. They are on the left. Actually, I should make it symmetric. So the first configuration, all the four particles should be on the left, and there should be no particle on the right. Right? So this can happen. You can arrange this particular situation in only one particular way. So that will be 4C4. If you see in the previous formula, that was capital N factorial divided by n1 let's say n1 n factorial and n minus n factorial. Okay. So this is the number of ways of arrangement. Here in this case, you have 4 factorial, out of which you are arranging all the 4 in the left side, right? So what you will get, this will be 1, and this will cancel out to give you 1. This is the first situation. Now in the second situation, let's say one of this particle is coming here. Now you don't know which one of this particle is coming here. So uh, so that you have the arrangement of particular arrangement of this LLR combination, so that it could be LLLR or LLRL or other possible combination. There will be 4 such possible combinations. How do you know? Because you are arranging three such particles out of 4 in this particular way, and the remaining 1 out of 1 particle in this particular fashion. So what we will get? We will get 4. There are 4 possible ways of doing this thing. And now in this, again in this situation, what you can do? In the third case, you have LLRR type situation. So you can arrange these 2 L out of 4 in this many ways, right? And the remaining 2 R out of 2 R, you can arrange them in 6 total. The total number of ways will be 6. You can do the rest of the exercise. Now, what will be the second question was, what will be the most probable state in which the system can be found? So, the most probable state, if you see, the probability corresponds to 6 by 16, right? So, that is this particular configuration is the most stable stable configuration, where half of the particles are on left side and half of the particles are on right side. So basically, this is corresponds to the ordered state. That is uniform distribution of particles, and that is what the equilibrium is. Now, the third part of the question says what will be the mean value of particle being at right. So you can find the expectation value of particle being on right by multiplying the number of particles that are on right with their corresponding probabilities. So in the first situation, how many particles are on right? So basically 0. In this situation, 1, 2, 3, 4. So we will be doing this, and corresponding probability we will multiply. So in the first case, there are 0 particles on the right, and the corresponding probability is 1 by 60. The second case, 1R, 2R, 3R, 4R, and I'm multiplying with their corresponding probabilities. So if you solve this, you will get the mean value of particle being on right will be as 2 times R, or basically 2. So now here the fourth question was how postulate of equal priori probability applies on this experiment. So basically what we have assumed that here we have total 16 combinations, and all 16 combinations will have equal probability. All equal probability. So this is an assumption. So we have never calculated this. This is an assumption which we make based on the principle of equal probability. So here in this situation also, this principle also holds that for an isolated system, which can be in any of this number of states, like 16 in this case, they all should be equally likely to be found in any one of the states. So you can also understand this concept from the deck of cards. Basically, you assume that the probability of getting any one of the cards out of the pack of 52 cards will be 1 by 52. Basically, you have never calculated this, but you assume that this is all probability of getting all these cards is equally likely. So here also, this is what the principle of equilibrium says. Now, let's come to the end by the ergodic hypothesis. This is one of the important hypothesis on which this statistical mechanics is based on. So what does this say? So basically, this is the fundamental concept in statistical mechanics and thermodynamics, basically, and this is the thing which bridges microscopic particle behavior with the macroscopic observables like temperature and pressure. So how does it do it? So, but it assumes that over a long period of time, so basically you will leave the system for a long period of time, and the time average of the system's observable, like just like energies or momentum, that will be equal to the ensemble average over all possible microstates. So basically, you have to take all averages over the all possible microstates of the system with the same energy level. So just in this case, if you have energy equal to minus E in the case of the magnetic spins, that is minus mu h. So in that case, you have up, up, down, and up, down, up, and down, up, up. So basically, this is the particular configuration corresponding to the same energy, right? Corresponding to the same energy. Now, if you leave this system for a long period of time, then the time average is like basically, let's say, energy of this system is equal to the ensemble average over all possible microstates. So basically, you will take ensemble average of all these three possible microstates, and then you will get this energy. So basically, let's try to understand this in simple words. So basically, if you watch the system for a long enough time, then you will explore all the states. So before finding the equilibrium, it will explore all these three microstates, and then only it will show the average behavior over time. That will match with the average across all possible configurations. Now, this hypothesis implies that the system's trajectory will eventually cover all accessible points in phase space, given enough time. So if you give enough time, then initially if it is up, up, down, then it may convert to up, down, up. And from that, it may convert to down, up, up. So if you give enough time for the system to respond. So that is what about ergodic hypothesis. Thank you so much for today, and we will meet with the next topic. Thank you for now.